So today we're going to be talking about finding the area under a curve, which is ultimately going to lead us to something called Riemann sums. Before we begin today, we're always going to start way back at the beginning. So I'm going to go back to some old geometry concepts. Do now, find the area of the shaded region. And we have a couple of pictures in front of us. I want to just kind of let you know up front, when we talk about a shaded region, we can also describe that as the area bounded by a curve, the x-axis, over a given interval AB. So in example 1 here, we have our curve, the x-axis, and our interval will be from 2 to 5. So that's basically what's going on here. So if we want the area of this shaded region, it's really easy to see that this area is just the area of a rectangle. So we can use a geometry formula. Area equals base times height. So our base is going to be 3 units, and our height is going to be 5. So our area here is 15, and we're going to go units squared, just to be good little math students. For number 2, I want the area of my shaded region, and now even though that's not a curve, we still consider it a curve. I know that seems silly, but so I'm going from 0 to 4. So my area would be, well, the shape here, again, a nice, easy geometry shape, the area of a triangle, 1/2 base times height. My area would be 1/2. The base is 4 units. And if you don't want to count boxes up, you can get the height of this by plugging in to your function. And my area of this shaded region is going to be 16 units squared. Bad shading. So our area is, there's my shade. My area is under this curve, so I'm going from here all the way to here. Now when I look there, I don't like what I'm seeing, because this shape, that's not really a triangle, right? So I have, does anyone remember this shape? Yeah, that's going to be a trapezoid, okay? And I'm sure there may be 1 or 2 people in this class that remember the area formula for a trapezoid, h over 2, b1 plus b2. H is my height, b1 and b2 are my bases. Now when we do it on the x-axis like this, it's a little weird. Our bases are going to go vertically, which is going to be a little bit, right? That's going to be my height. That's base 1 and that's base 2. Okay, so we have to sort of sometimes rearrange things a little bit from what we're used to. So my area here is going to be, my height is 4. B1, well, that's going to be the value I get when I plug 0 in, which is just 1. And B2 is what I would get if I plugged 4 into my equation, and that's going to be 5. So I have 2 times 6. My area here is 12 units squared. Okay, moving right along. Okay, now I want the area. Now I have 2 pieces. I have this triangle over here, and I have this triangle over here. Okay, let's start with this nice triangle here. Area equals 1/2. My base is 3. My height is 6. So my area for this triangle would be 9 units. And now when I move over here, 1/2, my base is 2, and my height is also, oh, no, my height is 4. Silly me. So the area of this piece is going to be 4. Okay. However, we have to start to understand now. I know that you're used to saying that area is always positive. Well, in calculus, area is negative if it's below the x-axis. So this is something kind of new that we have to sort of start to think about. So when we calculate the overall area of this shaded region, we're going to have 9 minus 4. So our overall area is going to be 5 units squared. Okay. Now let's move on to number 5. Okay. So number 5, if I go to calculate this area under this curve, okay, now I have a true curve. Okay. So this is going to be a little bit of a problem. I don't have a geometric formula to use. Okay. So when we run into this situation, we usually break it into shapes. Okay. And the first shape we start with in math is breaking it into rectangles. So this may seem a little weird, but you could calculate, or again, we're only going to be able to approximate this area. We're not going to be able to find an exact area for these just yet in math. But if I was going to make this into a rectangle, I'd have a lot of leftover area. Okay, so that's not, I mean, we're going to break it in, but what we're going to do is we're going to kind of piece this into a couple of rectangles. And basically the concept here is the more rectangles you break something into, the more you can approximate, or the better you can approximate the areas. So you'd break this up into rectangles, you'd find the area of each rectangle, and then you would add them up. So right now, we're going to go through a couple of new vocabulary and things to do, and then we're going to go back to this problem in just a few minutes. So our problem from the previous page was, what do we do when we're trying to find the area under a curve and we can't use geometric formulas? Well, what we're going to do is we're going to use something called a Riemann sum. And a Riemann sum is a way to approximate the area under a curve. And again, we want to kind of highlight, we're getting the approximate area. So let's say we have some given function, some curve, who knows what it is. And we want to calculate the area from A to some B. Basically what we're going to do is we're going to partition. Okay, so we're going to break this curve up into, let's say, we break it up there like that. Who knows? The more rectangles, the more partitions you make, the better your approximation. But it is a little bit time consuming. So basically, let's say we made our rectangles like that, right? So we would calculate this area, something like that. So if you notice, our area would be, a pretty close approximation. Okay. So now in order to evaluate a Riemann sum, we have to be told a few things. We have to know, or we have to be told, the given interval. Okay, and that's going to be described something like that, A to B. We have to know how many subintervals or partitions we're breaking this into. And we call that n. And that value is going to help us find the length of each base, which we're going to call delta x. So delta x is going to be b minus a, and then we're going to divide that by however many pieces we're breaking this into. And lastly, we need to be told whether or not we're going to use a left sum, a right sum, or a midpoint. Okay. So these are the pieces we know. And now let's connect this to see how we're going to get the area. So to get the area, basically what we want to do is we're going to start with our area formula, base times height. Now remember, the base is the length of each interval. So our base in math notation is going to be delta x. And our height of each rectangle is going to be the function value of what we plug in. So we can represent the height as f of x. And what we do now is, well, if I rearrange this a little bit, I get something like this. And delta x, remember, is the change in x. So in math, we can write that as dx. We want to add up all these areas. So we have a special math symbol in math, which means add up. And then somewhere over the years, this kind of turned into that big swoopy thing. And that became the math notation for the area under the curve. This is called a definite integral. Kind of looks familiar to the other day, right? This also means the antiderivative. So there's going to be a connection there, which we're going to see over the next couple of days. And just, this is the area bounded by the curve. X-axis on a given interval. Okay, so just some new vocabulary, some new notation. I do want to point out, we can evaluate a left Riemann sum, in which case you'd use the left side of each rectangle. We can use a right Riemann sum, in which case you would use the right side. Or you could use a midpoint. This is hard to see, but you can use the midpoint to get the height of each rectangle. Okay, so that's how you're going to decide what x value to plug in when you evaluate a Riemann sum. Let's go back to the original example. So I want to evaluate this left Riemann sum. Okay, remember, I'm doing the area under the curve. It went from 1 to 5. My curve was x squared. Okay, so I'm finding the area under this curve. I'm using 4 subintervals, so I'm going to break this up into 4 pieces. Okay, so now there's a couple of things we have to figure out, right? We have to figure out the length of each base. My length of each base is going to be b minus a divided by 4. So the length of each base is going to be 1 unit. So this one's going to be nice and easy. These are going to give me my rectangles. So basically, when I go to set up my formula using a left sum, the length of each base is 1. And now the height is going to be, I'm going to use the left endpoint here for my height. So I'm going to plug 1 into my formula. That's going to give me that rectangle. Then I'm going to go to the next rectangle. Base times height. That's going to give me that rectangle. Base times height. The next rectangle. Base times height. And that's going to be my last rectangle. So this area is going to be a little less than the actual area. But that's okay. We're approximating. Now, if I want to get the height of each one, I'm just going to plug the value into the function. I kept it a nice, easy function so we could do the math in our heads for the most part. F of 2 is 4. F of 3, 9. F of 4 is 16. Add these all up, and we should get 30 units squared. Remember, this is an approximate area. Okay. Let's do the same thing, but this time using a right Riemann sum. So in a right Riemann sum, now I'm just drawing this picture. You don't really need the picture, but I kind of want to get you guys to understand the concept. I'm taking that y equals x squared and going from 1 to 5 and just zooming in on the area I'm focusing on. And we can kind of just copy things from above. We already know the dx, right? Each base is going to be 1 unit. So now when I go to set up my right Riemann sum, area equals the base 1 unit times the height. Now for this one, I want to use the right side of the rectangle. So in this case, if you notice, your rectangle is going to kind of go like that. F of 1. Oops, F of 2. I'm using the right endpoint. Base times height. F of 3. Plus base times F of 4, right? We're using the right endpoints. Plus the base times F of 5 is going to give me the last rectangle there. And if we do the math part now, we're doing 1 times whatever we get when we plug 2 into our function. 1 times 3 squared. 1 times 4 squared. 1 times 5 squared. And if you add all these numbers up, you get your area to be 54 units squared. Well, as you can clearly see, there's a big discrepancy in the areas, but that's because we didn't use that many triangles, okay? I mean rectangles. But these two things are, again, just representations, okay? They're not the actual area. Lastly, we're going to evaluate the same function. We're doing y equals x squared from 1 to 5. We have 4 subintervals or 4 rectangles. So we already know from above the length of each base is going to be 1 unit. This time, however, we're using a midpoint. So we're going to go and find the midpoint of each interval, and that's going to be what we plug in. That's going to form our rectangles now. That's the height. So hopefully you're kind of seeing that this is going to probably give us a better approximation. And if we want to just, in the beginning, kind of identify what these will be. And all I did was went to the midpoint. It's very easy because the numbers are so easy to work with. So my midpoint setup would look something like this. Area equals base 1. Now the height is going to be f of 1.5. The second rectangle, my base is still 1, and my height is going to be f of 2.5. 1 f of 3.5, and 1 times f of 4.5. Remember, this is the height of each rectangle. It's an approximation of area. I don't want to waste too much of your time, so I did the calculations for you. And again, all I did was plug each of these numbers into the given curve. And our area becomes 41 units squared. So this is just a little brief introduction to Riemann sums. We're going to continue on tomorrow. Before I leave you though, if I asked you to describe each of these as a definite integral, remember our curve is y equals x squared, so we could say all of these approximate the area from 1 to 5, and it's the area under x squared dx. We're going to talk about this more in the upcoming days as well. Okay? Meet you all tomorrow. Bye.